Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to have 46th lecture and 10th module of this course. Before going to the contents of this lecture, let us quickly recall the contents which we learned in the last lecture. All of you knowing that iterative methods plays a vital role in science and engineering applications. So therefore, there are a lot of things to learn from iterative procedures. Today we are going to learn some iterative techniques for linear systems and what do you call conjugate gradient method. In contrary to the regular iterative methods such as Gauss-Jacobi method, Gauss-Seidel iteration method, successive over relaxation method. The important point which we can note down here is not all iterative methods for the solution of linear systems are based on the notion of splitting and the conversion to a fixed point problem. For example, there is a completely separate class of techniques based on the equivalence between the solution of a linear system and the minimization of an associated quadratic functional. The conjugate gradient method, which is popular choice for the solution of large spare systems, belongs to this class of technique. The moment when I speak spare systems, that means zeros are dominant over non-zero entries. Minimizing a quadratic functional and solving a linear system. Suppose A is a symmetric and positive definite n over n matrix, that is a square matrix. The assumption will be made throughout the section considering the mapping F maps R and to R defined by this mapping. F of x is 1 by 2 times of x transpose Ax minus B transpose of x plus a constant called C. Mathematical objects such as this, which operates on the components of a vector to produce a scalar output, is referred to as a functional. So let me repeat once again. A mathematical object such as of times of x transpose Ax minus B transpose of x, which operates on the components of a vector to produce a scalar product or a scalar output, is usually termed as a functional. In particular, f happens to be a quadratic functional. Minus x transpose Ax consists of a collection of terms, all of which are of degree 2 in the components of x. Under the assumption that A is positive definite, f behaves much like an upper bound opening parabola and hence has a unique global minimizer. There exists a unique vector x star such that f of x star is less than f of x. For all x belongs to R of n, x not equal to x star. From basic calculus, we know that the location of the minimum value of f can be determined by the gradient of this vector. Del of f is equal to df upon dx1 times of df upon dx2 times of df upon dx3, so on and so forth, df upon dxn whole transpose. To be identically 0 when evaluated at x is equal to x star. In terms of the elements of A and the components of x, we can write like this. Fx is equal to half times of summation I is equal to 1 to n xi multiplied with summation j is equal to 1 to n aij xj minus of summation j is equal to 1 to n bj xj plus cj. Therefore, for each k you will have the equation df upon dx of k will be equivalent to 1 over 2 times of summation I is equal to 1 to n xi aik plus summation j is equal to 1 to n akj times of x of j minus b of k. That will be equivalent to 1 over 2 times of summation I is equal to 1 to n aki xi plus summation j is equal to 1 to n akj xj minus b of k. So that will be equivalent to summation j is equal to 1 to n akj xj minus bk, that will be equivalent to ax minus b of k, where the symmetric of A was used in going from the first line to the second. So therefore you will have, that is del of f will be equivalent to ax minus b. And locating the minimum of f is equivalent to solving ax is equal to b. So how do we numerically approximate the global minimizer of the functional f? Most of the techniques developed for this problem start with an initial guess, that is x of 0, and then generate the sequence x of m according to the equation x of m plus 1 will be equivalent to x of m plus lambda m times of d of m. The vector d of m is called the search direction and the scalar lambda m is the step size. Of course, different minimization methods are determined by different choices of the step size and the search direction. We will now turn our attention to a discussion of the step size and the search directions which define the conjugate gradient method. Choosing the step size, suppose that the approximate minimizer x of m and the search direction d of m are known, we will apply the following basic principle to determine the corresponding step size. So we will select lambda m so that fx is minimized along the lines x of m plus lambda times of d of m, substituting x is equal to, that is equal to x of m plus lambda times of d of m into f of x gives f of x of m plus lambda times of d of m will be equivalent to 1 over 2 times of x of m plus lambda times of d of m transpose multiplied with a of x of m plus lambda times of d of m. So that will become, when you simplify this, it will be 1 by 2 times of x of m transpose a x of m, that is the first term, plus 1 by 2 times of lambda of d of m transpose a x of m, plus third term is 1 by 2 times of lambda of x of m a dm, plus this is the another term, and this is the minus of b transpose x of m minus of b transpose lambda times of d of m plus c. So when you simplify this, you get like this: 1 by 2 times of d of m transpose a d of m lambda 2 plus 1 by 2 times of d of m transpose a x of m plus 1 by 2 times of x of m transpose a d of m minus b transpose d of m times of lambda plus 1 by 2 times of x of m transpose a x of m minus b transpose x of m plus some constant c. Since the matrix A is symmetric and for any two vectors u and v, then u transpose v is equal to v transpose u. It follows the equation like this: x of m transpose a d of m is x of m transpose a transpose d of m, which will be equivalent to a x of m transpose d of m, which is d of m transpose a x of m. And b transpose d of m is d of m transpose b. Therefore, we will have the equation like this: f of xm plus lambda times of d of m is 1 by 2 times of d of m transpose a d of m lambda square d of m transpose a x of m minus d of m transpose times of b plus c. So finally, you do arrive this equation, where c is equal to 1 by 2 times of x of m transpose a x of m minus b transpose x of m plus c, and r of m is equal to a x of m minus b. Note that Rm is just the residual associated with the approximation x of m. The positive definiteness of A guarantees that d of m transpose a d of m is greater than 0 for any d of m not equal to 0, which implies that f of x of m plus lambda d of m is upward opening parabola, that is lambda times of x of m plus lambda times of d, then that achieves the minimum value when this value happens to be 0. So df by d lambda is d of m transpose a d of m lambda plus d of m transpose r of m is equal to 0. So finally, we do arrive this equation: lambda m is minus of d of m transpose r of m d of m transpose a d of m. Now choosing the search direction, as the name of the method implies, the search directions in the conjugate gradient method are based on the gradient of f. Recall that we will have this delta f is nothing but ax minus b. Then we will have the delta of f of x of m is ax of m minus b, which is r of m, the residual vector. To simplify the notation in the derivation that follows, we will therefore r of m usually in the place of delta of f of x of m when referencing the gradient. For the iteration of the conjugate gradient method, the search direction is chosen: d of 0 is equal to minus r of 0, which implies x of 0 travel in the direction opposite to that of gradient. Standard arguments from multivariable calculus guarantees that this is the direction of maximum disease in the value of f. All subsequent such directions are determined like this: d of m plus 1 is minus of r of m plus 1 plus alpha m times of d of m for every m greater than or equal to 0. The scalar alpha m is chosen so that the direction d of m plus 1 is a conjugate direction in the direction of d of m. So let A be a symmetric and positive definite matrix. Two vectors u and v are a conjugate if the happens to be u transpose av is equal to 0. Thus, to determine the formula for alpha m, we start by computing these values, that is d of m plus 1 transpose a d of m is equal to minus of r of m plus 1 plus alpha m times of d of m and a d of m. So, which will be equivalent to minus of r of m plus 1 transpose a d of m plus alpha m times of d of m transpose a d of m. For this last expression to be 0, so we see that this expression is like this. Alpha m is r of m plus 1 transpose a d of m divided by d of m transpose a d of m. The matrix vector product a d of m and the vector product d of m transpose a d of m would readily have been computed as a part of the calculation of the step size lambda m. So, the calculation of alpha m requires only one additional vector product and one division. So, gathering together the approximate solution updating equations, the step size, so we will have this r of 0 is equal to, that is ax of 0 minus b, and d of 0 is this, and for m is equal to 1, 2, etc., we will have these expressions in terms of lambdas. So, lambda m is this and x of m plus 1 will be this. So, this is the eigenvalue and this is the eigenvectors. So, we can write this r of m plus 1 is equal to ax of m plus 1 minus b. So, you write like this tolerance and d of m plus 1 is really like this. The inputs to this routine are the coefficients of the matrix A and the right hand vector, B the initial vector x naught. And the convergence tolerance will be tolerance. The first two lines set the initial search direction inside the iteration loop. The step size updated approximate solution of the residual are given as like this. If the length of the new residual is not below the convergence tolerance, the new search direction is computed for the next iteration. Making the algorithm more efficient, the pseudocode that was presented above for the conjugate gradient method is not as efficient as it could be, that each iteration technique requires the calculation of two matrix vector products. So, we will have the new residual r of m plus 1. So, r of m plus 1 to be calculated from the old residual Rm and taking the advantage of the principal residual vectors and the directions. Let us see how r of m plus 1 can be calculated from r of m. Take the approximate solution and updating this equation like this. X of m plus 1 will be equivalent to x of m plus lambda m times of d of m. Multiply through the a and then abstract b from both sides, this produces the equation like this. Ax of m plus 1 minus b is ax of m minus b plus lambda m times of a d of m. Applying the definition of the residual vector, then yields this vector. So, equation 1 still requires a matrix vector product, but this is the same matrix vector product needed for the calculation of both lambda m and alpha m. So, you will have a further the efficiencies can be gained by developing different formulas in this following equation as needed. So, first take the equation 1 and multiply by d of m, so which will give you this expression d of m of transpose r of m plus 1 is, and this vector, and similarly this vector is this vector and turns out to be this 0. So, the previous such direction and the new residual vectors are orthogonal with alpha m chosen to make the such directions. So, you will have this value. So, r of m transpose r of L is equal to 0 for all m is not equal to L. So, solving the equation 1 and AD, which will give you this kind of expression, that is 1 by lambda m times of r of m plus 1 minus m, and if you pre-multiply that, ultimately you will end up with this matrix. So, where lambda m is not equal to 0. So, you will have 1 by lambda m is r of m minus alpha m minus 1 d of m minus 1 transpose r of m. So, you will have the matrix like this, 1 over lambda m, r of m and r of m whole power r. In going from the first line to the second and from the third line to the fourth, the orthogonality of the previous such direction, and it becomes a matrix, a value like this. So, that is lambda m is nothing but Rm transpose R of M upon D of M transpose A D of M. The vector product R of M transpose R of M transpose R of M will have been computed for the convergence test during the previous iteration. So, the new formula lambda M saves one vector product over the original formula. So, you will have pre-multiply, you get like this, that is R of M plus 1 transpose AD of M is 1 over lambda M R of M plus 1 transpose multiplied with R of M plus 1 minus R of M. So, ultimately you will have 1 by lambda M R of M plus 1 transpose R of M plus 1. So, where the term R of M plus 1 transpose R of M has been eliminated by applying the orthogonality of the residual vector, dividing 4 by 3, so you get the vector like this. Alpha M is R of M plus 1 transpose R of M plus 1 upon R of M transpose R of M. This formula reduces the operational count for each iteration of the conjugate gradient method by one or more of the vector product. Taking into account the new formula for R of M plus 1 lambda M or alpha M, we arrive at an efficient algorithm for the conjugate gradient method. So, you will have R of 0 is equal to Ax of 0 minus B, and D of 0 is nothing but minus R of 0. Now, if you set that lambda 0 is R naught of transpose or 0 for M is equal to 0, 1, 2, etc. So, you set U is equal to AD of M, then lambda L will become delta M upon D of M transpose. So, they iteratively you get the M plus 1th iteration. R of M plus 1 is nothing but R of M plus lambda M times of U. So, if you set the tolerance like this, you get what you call this the square root of delta of M plus 1 is less than tolerance, and output is X of M plus 1. So, this algorithm requires only one matrix vector, two vectors products, and three vector additions per iteration. So, the complexity of the algorithm is like this. So, therefore, we will see some more examples in the next lecture, and today what we did is some fundamentals and some mathematical calculations related to the conjugate gradient method as a iterative technique. Thank you very much for listening to my lecture. So, again I will get back to you in the next lecture, some few examples. Thanks you once again.